In our previous video, we looked at doing a linear trend to forecast data. We are continuing to look at trend forecasting, but here we'll look at polynomials. So if you're working alongside us in Python, you can go to drstephpowers.github.io/management in Python. Click on the forecasting button here. It'll take you to GitHub, open in Google Colab, sign into your Google account, and save a copy so that you can edit it yourself. So we click here on forecasting. Ultimately, you end up inside this Python workbook. In our previous video, we did a linear trend. And so we had our complaints and the number of periods that we were looking at forecasting what the complaints would be for our company in the future. So we had taken our data and we had put it into a table, and we had previously fit a linear regression, forecasted into the future, and got a formula as well. And we looked at how well the model fit, and it had an R-squared of about 63%. We plotted the information. Here we had our linear forecasted trend and the forecast into the future. Well, since this has some issues here, perhaps a polynomial might fit better than a line. So when we look at different types of forecasts, you have forecasts that are linear, right? So we can go up. Likewise, you can have a linear forecast that goes down. You can have a polynomial. So a polynomial of degree 2 would look like this, or alternatively could look like that. You can have polynomials of more than degree 2. So here we have 1, 2, 3, polynomial of degree 3. It can also go the other way. Okay, 1, 2, 3. So this is polynomial of degree 2. This is polynomial of degree 3. And you can have even more waves, basically higher degree polynomials every time it turns. So see, this is 1, 2. This is 1, 2, 3. As you add more turns to the graph, you're adding other degrees to your polynomial. So let's take a look at a polynomial and try to fit it to our same complaint data. So if you did not run the previous video, you will need to run a couple things. So first, what we're going to need is to import pandas as PD and numpy as NP. Then what we're going to need to do, I'm just trying to find the trend section here, is that you'll need to import matplotlib.pyplot as PLT for our graphing, and then we'll do the sklearn.linear model as well. So we entered in our complaints, we entered in our periods, we turned it into a table, and so here we have our table of complaints. So make sure you run that code if you didn't run the previous video. Now, to do a polynomial, we need to define the polynomial. You can call it whatever you want. Here I just called it AB. Anything is fine. We are going to use numpy. We are going to call the command polyfit, so it's going to fit a polynomial. Our x values are going to be the periods from our complaint table. And we are going to predict complaints from our complaint table. So CT and then hard brackets says what column we're pulling it from. And let's start with a polynomial of degree 2. So that means when we do a polynomial of degree 2, it's either going to look like this or it's going to look like this. Okay? All right, let's run that. So it's going to fit a polynomial of degree 2. And now we need it to create a function from that information. So the next lines of command here say create a function, and it's using poly1d. So it's going to create that polynomial function from your fitted model we called AB. Okay, so if you leave this as AB, all you have to do is change the CT period and CT complaints to your own data set. You can run this function just as is. And we want it to forecast, so we want it to predict values of y using that function and we wanted to predict the actual values, or wanted to predict the values using the periods. So essentially, by you're creating your forecasted function, it's going to predict the y values from your x's, and then later we'll do like we did in the previous video. We'll give it new values of x's to predict the future. Okay, so we're doing our curve of best fit, and then we'll put it out to the future. So we've ran this one, run this one. We can actually add a line of code here. We can say, okay, func, give me C. And what this gives me is the coefficient. So if I wanted to write the formula for this, so my y, which is my complaints, call y here, is equal to, and then it does it in reverse order. So it's saying 6.107 minus 4.607x plus 0.917 x squared. Okay, so that's what it's telling you is the formula. So what this means then is that our graph, when we look at it, is going to go down, then it's going to go up. It's going to start here at 66, it's going to go down, and then it's going to go up. Now, we want to know how well this formula we've just created, how well it fits. In the previous video, we could just simply call from the linear regression model, we could call something called score. So we had named our linear regression model equals linear regression. We had fit the linear regression, and we could simply call model.score, and it gave the r squared. You can't do that with the polynomials. It doesn't have a built-in r squared. So instead, we have to define r squared. So I'm doing that for you, which means if you're doing this for your own data set, all you have to do is copy this. So we're going to define compute r squared, where it has the true value for y and the predicted value of y. And then it does the r squared formula. So when we're looking at this, SSE, this is the sum of squared error, difference between the true and the predicted, squared and summed. And it's going to take that and compare that to the total sum of squares. And the r squared calculation is 1 divided by the sum of squared errors divided by the total sum of squares. Well, what does all that mean? It doesn't matter. Copy it as is, this whole definition here, recognizing that in order for it to compute r squared, you have to give it the true values for y and your predicted values for y. So you just take this formula as it is. We've defined it. Now we can have it compute r squared for our complaints polynomial of degree 2 model, where it's going to compute r squared using our true y's, which is the complaints from the complaint table, and it's going to use the predicted values of y that it got from that function, this complaints function, that's a polynomial. So here we just simply call this definition compute r squared, and we tell it what to use for the true y and the predicted y. And we get an r squared here of 0.79. So that means that 79% of the variability in the number of periods explains the variability in the number of complaints. Notice that this model fits better than the linear model we saw in the previous video. Now we need to follow the same process we did in the previous video, which is we need to give it some x's for the future, because our table only went to period 8. So let's give it x2 is equal to 9, 10, 11, and let's make it an array. Notice you don't have to reshape it, because that was only the linear regression command. You don't have to do that for the polynomial one. So x2 equals np.array 9, 10, 11, and then find the predicted values using that polynomial function we found up here, using that polynomial function applied to that new 9, 10, 11. So what we get is that for period 9, 10, 11, the forecasted values are 98.89, 111.7, and 126.34. Notice they're a lot bigger than the linear one. So the linear one here that we looked at in the previous video had predicted 85, 88.78, 92.42. This polynomial is predicting much larger numbers. So let's look at it on the graph. It makes it easiest to see. So let's plot the period, so CT, complaint table, column period, against the complaint table complaints. So X values are the periods, that's the horizontal. Complaints are the vertical. Let's not have a line, let's just put dots for the actual data. Then let's plot the number of periods times the predicted y's that came from our polynomial of degree 2, and let's make it a nice thick line so we can see that predicted model. And then let's also plot the new values for our periods 9, 10, 11, and the predicted complaints that go with them. Let's make those dots, and let's add a dashed line so we can see those. We can add an X label of period. We can add a vertical label of number of complaints. You can even add a grid to it if that makes it easier to see. And we can run that. Okay, so notice what we said previously with our number of complaints. It would start at 66.107, it would go down, and then it would go up. So if we look here, starts at 66.7, goes down, and then goes up. So our polynomial of degree 2 looks like this one here, down then up. Okay, and that means that the forecast for the future is all up. Okay, so polynomials have wiggles to cover historical data, but the future data only goes one direction, either all up or all down. So in this case, it fit the historical data 79%, but it doesn't tell you how well it fits the future data. For the future, it's assuming 98.89, 111.7, 126.3. So it's assuming the number of complaints in the business goes up substantially in the future. So we have forecasted some future periods. We have come up with a formula to show that relationship between time and the number of complaints, and we have calculated the R-squared to see how well they fit. We could look at other polynomials. This is a polynomial of degree 2. Perhaps a polynomial of degree 3 would fit better. So we're going to follow the exact same process we just did. The difference is that our AB here, which is fitting our polynomial, instead of it being a polynomial of degree 2, we can make it a polynomial of degree 3. You'll notice the rest of the code is the same. So if I just go back up so we can show here, we fit the polynomial. Before it was degree 2, now we're going to do degree 3. We find the function for the polynomial. We forecast the y values. We predict the y values using that function. We then compute the R-squared. We've already defined R-squared once. We don't have to define it again if we've already run this code. And then we gave it some additional X values and had it then predict the Y's that went with those new X values and put it all in a graph. So let's do that. Fit the polynomial of degree 3, find the function, okay, predict the values using that function. We could add to this, just like we did before, you can use func.c, and you can actually get the formula for here. And it's going to be in reverse order. So if we were to write this out, this says the number of complaints, so that's our y, is equal to 66.107 minus 4.607 x plus 0.92 x squared. All right, I should have more numbers there. Let's make sure I've run everything. So let's change that up. Let's see, did I run this? polynomial of degree 3. Rerun that. Rerun this. There we go. It didn't match. We didn't have enough. So you want to make sure you run all the pieces. All right, so let's rewrite this out. This is 83.36 minus 22.55x plus 5.62x squared minus 0.35x to the third. Woo. And I seem to be super inconsistent on whether my x's are capitalized or lowercase. All right. So what does that tell us? That means that the function it just found is going to start at 83. It's going to go down, then up, then down again. All right, how well does this model fit? Well, we can call the R squared, compute R squared calculation, use our complaints, and use our new predicted Y. So notice that it fits even better, right? 0.876, 87.6% of the variability in the time explains the variability in complaints. So it seems to fit even better. Well, the higher you go for polynomials, the better they always fit because they match every curve in the data. But again, it doesn't mean that it matches well for the future. So to see the future, let's create an array of x values that is 9, 10, 11, and then have it take our new function, our polynomial of degree 3, and calculate or get the predicted values for y. Okay, so when period 9, it's predicting 81.6. For period 2, it's predicting 71.45. And for period 11, it's predicting 51.59. So we had said that with our polynomial of degree 3, right, it either goes up, or down, up, down. So when we looked at our formula here, it was down, up, down. So we can plot this information and see if that matches. So we're going to plot the actual data, so our periods and our complaints, and we're going to put those as dots, no lines. Then we're going to plot the actual periods with our forecasted y values. That's going to be our polynomial of degree 3. We'll make that a nice thick line. And then let's plot our period 9, 10, 11 in the future and the predicted y's that go with it. Let's make those dots with a dash. We have our x-axis labeled period, our y-axis labeled number of complaints, and if you want to add a grid, you can do that too. It's thinking about it. All right. So remember, we said it would start at 83 and go down, then up, then down. So it's going to start here. It's not quite 83. It's showing here. Down, up, down. So that same curve. Okay. You can see here the blue are the dots for the actual data. The orange is the fitted polynomial of degree 3. And the green is the forecast for the future. So even though this model fits better, because it's starting to match all the different curves of the actual historical data, notice that the future just assumes complaints drop. The previous one just assumed the complaints went straight up. And so that's true with polynomials. All the future forecasts are either keep going up or keep going down. Doesn't matter how many historical curves you add, the future is only one direction. So that means that when you think about, should I have an even more complicated polynomial, you have to think first, can I explain to the stakeholders what this formula means? Can I explain why in this time period it went down, then in this time period it went up, and in this time period it went down? Does that make sense? Is that too complicated? To get a higher R squared, but lose the ability to explain it, to make it more complicated to calculate it, to make assumptions like suddenly it just drops to nothing, is not necessarily worth the higher R squared. So keep that in mind as you look at more complicated polynomials. Before we leave the topic of polynomials, Let's just do one more. Let's look at polynomial of degree 4. So exact same code. We fit the polynomial. We're just changing this to 4 degrees instead of 2 or 3. So let's run that. We then say, okay, use that information to find the function and predict the y values. You could, just like I did before, you could add in that func.c and get the actual values for the formula. So what is this? This is complaints is equal to 51.86 plus 23.74x minus 14.56x squared plus 2.99x to the third and minus 0.19x to the fourth. Okay, so it's going to start around 51.86. It's going to go up, then it's going to go down, then up, then down. Okay, so quite a wave here. How well does that fit? Well, let's call that compute R squared calculation. And now we're sitting at 94.7%. The previous polynomial was 87.6, and the one before that was at 79.4. So notice the R squared is always going up because we're matching every single movement of the historical data. Okay. We are then going to have it take in a new set of data. So this is going to be those future x values, future periods 9, 10, and 11. Turn that into an array. Then take that information, put it into the function, and find the predicted values for that new data. What we get is in period 9, it's 50. In period 10, it's negative 30. And in period 11, it's negative 183. So complaints drop to negative numbers. So notice that the polynomial of degree 4 fit really, really well historically, but does the future forecasted values make any sense? We can plot it, so we can plot the actual periods and the actual complaints, make them dots, no lines. Plot the periods and the predicted values, that's our polynomial of degree 4, make it a nice thick line, line width 2. Then plot the future data. Those are the x2 values of 9, 10, and 11, and its corresponding predicted complaints. Make those dots with a dashed line and add it to our graph. If you want to add grid lines, you can do that too. And we can plot the information here. So notice it fits the old data really well, but the future data, it turns into negative complaints, which we know aren't possible. So even though the polynomial of degree 4 fits really well, it doesn't actually make any sense. And so when you're doing forecasting models, you have to think about how complicated is the model? Can I explain it to the stakeholders? Is it easy to do a calculation? Does it make sense for the future? And consider the R squared. Don't consider just the R squared by itself.